Saxon Advanced Mathematics. Welcome to Lesson 18. We're going to do a catch-up on all the different kinds of word problems that we have studied in the past. And I am not going to lie, this lesson is a marathon. There are 7 different types of examples. 7 different types of problems. It's a lot. So you can take a break halfway through, and I'll remind you of that. All right, the main thing I want you to hold on to hold in your mind, is that the number of variables, that's a number sign. The number of variables is equal to the number of equations that you need. For every variable you have, you need an equation in order to solve it. So a big part of these problems is being strategic about how we set up the variables so that we don't have to set up a million equations. Ready? First one. The number of blues was 4 less than the sum of the whites and the greens. Also, the number of greens equaled the sum of the blues and the whites. How many of each were there if there were twice as many blues as whites? Is your head spinning? Mine is. But here's what I took away from that inspired reading. There's blues and there's whites and there's greens. And so that's 3 different colors. And they told us 3 different relationships among them. So I can go back and turn each of those into an equation, and then I'll have 3 variables, 3 equations, and I'll be happy. The number of blues, so I'm going to do the subscripty thing. The number of blues was less than, I'm going to use the trick where I ignore the number of how many less and just write it as an inequality. The number of blues was less than the sum of the whites and the greens. Number of whites plus number of greens. Okay? And now I go back. Now that I've written the inequality, I'm going to fix it. This side is bigger, that side's smaller. I'm going to subtract from this side because I like to write it on this side. So I'm going to subtract 4 is the balancing number. And now I can turn that into equals. All right. That's the first one. Also, the number of greens equaled the sum of the blues and the whites. Interesting. And then the last one, there were twice as many blues as whites. Again, this is another one. Be careful, write it as an inequality. There were twice as many blues as whites. Twice as many means we have to multiply something by 2. I'm going to do it right there. This is tricky. We want to say, oh, there's twice as many blues, so it's 2 times the number of blues. No, it's the other way around. That's confusing always. So write it as an inequality and then fix it. Okay, now, there are lots of ways to solve this, and I encourage you to follow whatever works for you. What I'm going to do, what occurs to me, is I'm going to put, let's do these A, B, and C. I'm going to put this equation into A and B. That will knock out the NB, the blue variable, and everything will just be stated in terms of W's and G's. Then I should be able to solve it more easily. So my first step, substitute C into A and B. All right, so my new A will be 2 times the number of whites, right? Because this is what I'm putting in for there, equals the number of whites plus the number of greens minus 4. And then my second one will be the number of greens equals 2 times the number of whites plus the number of whites, right? Because this goes in there, and then we just have that. All right, I like it. Now, for my next step, I obviously have to clean this up, rearrange it, right? And so I'm sitting here thinking, how do I want it to look? And the way we often like our systems of equations to look is we have the first variable plus the second variable equals the constant. So I'm going to reshape both of these so they look like this. All right, that means I've got some swimming to do. So that's going to be, let's see. Oh, wait, I put N. That's not helpful at all, is it? It's W. Oh no, it's a W. It's just a squishy W is what happened there. Okay. So I'm going to subtract everything and move it this way. I'm going to put the G's first. That's going to be negative times the number of greens because I'm swimming him over. Then I'll swim him over. That's going to be subtracting, so that'll be 1 number of whites equals -4. Still sitting over there. Make sense? And then I'll fix the second one. And again, I want the G's first, so it'll be NG. And then it'll be, this turns into 3NW, right? So it'll be -3NW equals 0. There's no plain numbers in there at all. Okay. So now I see it's all set up. Step 4, I'm going to, or step 3 rather, I'm just going to add them because they'll eliminate, won't they? They'll be perfect. I'm excited about that. I'm going to copy them to the top of the next page. And then okay. Get my book lined up again. All right. So this is just me copying forward. Step 3, I think, is what we're up to. I'm going to eliminate. And I'm excited about that because I can see it's already good to go. So when I do, it will be -2 times the number of whites equals -4. And I get that the number of whites equals 2. Yay! I like that. And then remember that when we're eliminating, we look down the columns and look and see which one sets us up better to eliminate. Substitution, we look more at the rows. For elimination, we look down the columns. Okay, step 4. Solve for all variables. I can see I've got 2 equations right in front of me, and I can use either one of them to solve for NG. So let's do this one. -NG plus 2 equals -4. So I'm going to subtract 2, sorry, from both sides. And I'll get -NG equals -6. So then I get the number of greens equals +6, right? Because I can multiply or divide, however you want to look at it, both sides by -1. And then I have to go hunting for an equation that will give me the number of blues. Oh, here, this will work easily, right? Number of blues equals 2 times the number of white. So number of blues equals 2 times the number of white, which is 2. So we get the number of blues equals 4. Blues 4, green 6, whites 2. Yay, that's all the right answer. And I'm just going to box it like that. Neatness counts, but I don't like to keep writing my answers over and over and over. That's a great way to make mistakes. Okay, beautiful. That's 1. Let's move on, shall we? $18.2. The quarters, nickels, and dimes totaled 20, and their value was $1.90. How many of each kind were there if there were 4 times as many nickels as quarters? Okay, it's a coin problem. We know that there's going to be a quantity statement and a value statement. And because this one has 3 variables, 3 different kinds of coins, we're going to have one more statement of equality to write about. Now, just for variation's sake, this time, instead of using subscripted variables, N, Q, N, D, N, N, I'm just going to use the letter of the coin name. So, quarters plus nickels plus dimes equals 20. And their value was $1.96. Okay, so let's see if I can remember all the tricks to this. We have to multiply each one by the value of its coin. And we have to restate the dollar amount in cents, so that means we have to, well, it's not 20, it's $1.90, $1.90? Yes, $1.90. So I have to make that in cents 190. Otherwise, I have to put decimals and everything in. No, thank you. I'd rather do it in cents so that I have no decimals. And then the last one, if there were 4 times as many nickels as quarters. Okay, so again, write it as an inequality. There's more nickels than quarters. If there's 4 times as many nickels as quarters, then there's more. I don't need to multiply this by 4. I need to multiply that by 4. Make sense? All right. Now we have to decide on a strategy. Again, there's lots of ways to do it, but when I see this, when I see one variable set up as equal to another one, that makes me want to substitute. So I'm going to do the same thing we did last time. Step 1, substitute, and let's give them letters, A, B, and C. Let's substitute C into A and B. All right, so A, the new A becomes Q plus 4Q plus D equals 20. And the second one, B, becomes 25Q plus 5 times 4Q plus 10D equals 190. All right. I'm just checking my numbers. All right, what I would like to do now is I would like to clean up both of these. I can add like terms here, and then I need to do a multiplication, but I can add like terms there. So, step 2, clean up. And again, I want to arrange them into, I guess I'll do quarters plus dimes equals the plain number, the constant. Okay, so I'm going to have 5 quarters plus dimes equals 20. And I'm going to have, let's see, this is 20Q. So this becomes 45Q plus 10 dimes equals 190. So now I'm going to have to do something to make these eliminate, or I suppose I could substitute again, but you know, once is enough for me. I would say let's eliminate. And let's do that by multiplying this one by what? Let's multiply by -10 because it's easier to multiply by 10. I could multiply it by -9 and that would make the q's cancel, which is fine, but I'd rather multiply by 10. I think I will be error-free if I do that. Okay, so I'm multiplying the top row by -10. Minus 50q minus 10d equals -200. And then the second row we leave the same. 45q plus 10d equals 190. This is going to cancel, and I'm going to get minus 5q equals -10. Ready? I'm going up top. Minus 5q equals -10. Yay! That looks so solvable. So now I get that the number of quarters equals 2. And then my last step, which one am I on? Step 4. Solve for other variables. And let's see, I know that the number of nickels equals 4 times the number of quarters, right? So the number of nickels, I didn't need to write it like this, my brain went into that mode. It's going to be 8, right? The number of nickels equals 8. And then I know that they all add up to 20, right? Because that's where we started. Quarters plus nickels plus dimes equals 20. And so 2 plus 8 plus d equals 20. And that means that the number of dimes must equal 10. And that's the right answer. And again, I'd rather have a wacky box around my other information than rewrite it. And that's correct. Yay! How's your brain feeling so far? All right? Okay. Lesson 13. Or not lesson, example 13, talks about variations. I'll start on a fresh page. It's one of my dilemmas. Should I start on a fresh page or try to use up the rest? It doesn't matter. Better to just have more white space. Okay, variations. I want to give you a summary of everything we've learned about variations. Let's make a chart. You know as soon as I start drawing boxes that I'm off-roading and John is not with me. John doesn't do a lot of box charts like I do. Okay. We'll see if I got this right. We learned that there are 2 kinds of variations. There's direct variations and there's inverse variations. We also learned that there are 2 kinds of ways you can approach these problems. One is you can solve for k, which is a constant, and the other way is you can use a ratio of like before and after. Okay, so here we have the 2 types of variations, the 2 strategies we have for solving them. What we learned is that with a direct variation, you can find a constant and it flows in that pattern. If it's an inverse variation, it looks like this, right? You make a fraction. Cool, right? Then we learned this whole ratio or proportion way of doing it. We take the beginning over the ending number of the same thing, and we compare that to the beginning over the ending of the other thing. All right? And then the ratio method is kind of cool because you take first over second and then you flip. Right? Notice this is B1 1 over 2, 1 over 2, but down here it's 1 over 2, 2 over 1, what? Okay? Now, that's a good summary of everything we learned up to a point, but then we started squaring things. And that just adds a whole new level. So I call these simple variations, and I call these squared variations. And they aren't too different, but they just sound scary when you read about them. Okay, so that's how we could incorporate a squaring into the constant style formula. And if we were incorporating it into the other kind, we would just add it in there. Okay, and then the same thing for flipping it. This isn't all that different from what you might mentally think, but the problem is that when we get in the middle of it, and then sometimes we combine them, it can make your brain explode. So I wanted to lay out all the options in front of you, this is variations, before we start our problem so that you can really have all this in front of you and make your choices about what you want to do. Example 18.3. Oh, one other thing I wanted to point out is that when you use the constant method, the problem becomes a two-step process where first you solve for k and then you use k to answer this question. With the ratio method, you don't have to solve for k. You're just filling in all the before and after data into these proportions. However, we very often want to rearrange the formula and get the variable that we're solving for by itself before we go into too much drama. And that's what we're going to, no, I don't think we need to do it in the first one. Let's read the example for 18.3. Reds vary directly as blues squared and inversely as greens. And then it starts in with the numbers. So let's just figure that out. You follow along what the sentence says. Reds varied directly as blues squared and inversely as the greens. That is the way my brain most easily and naturally understands that. I can do the ratio method, but my brain wants to do this first, okay? When there were 80 reds, so now we're gonna solve for k. When there were 80 reds, there were 4 blues and 2 greens. And then it gives us more information, but we can stop here and solve for k. Now we could rearrange this. Let's just go ahead and do the algebra as it is. 80 equals k times 4 squared all over 2. All right, this is 16, right? 4 squared is 16. 16 and 2, we can simplify that with an 8. I'm gonna circle that because it's gotten confusing, a lot going on. But now all I have to do is just divide both sides by 8. So we get k equals 10. Oh, that's so cute and easy, right? All right, now we're ready to go back to the formula. Now we have a value for k. We're gonna plug in 2 of the 3 that we're given and solve for the third one. All right, so I'm gonna copy this and this to the top of the next page. R equals k b squared over g, and k equals 10. That's what we know in our scenario. Now let's get the information. How many reds are there when there are 8 blues and 10 greens? All right, we plug in what we know. R, and John, see, we don't have to rearrange because John already has us trying to figure out the thing that's by itself anyway. K is 10, B is 8, that gets squared, and it's all over 10. Well, this is pretty easy because those 10s cancel, and this becomes 64, so we say R equals 64. Yay, that's the right answer. Let's move on. This is a problem style that we learned at the end of last year. It's the kind where we talk about the units, the different values. 18.4. The sum of the digits of a 2-digit counting number is 5. When the digits are reversed, the number is 9 greater than the original number. What's the original number? Okay, this is where we have to be careful and set it up right. The T is going to equal the digit in the tens place, and the U is going to equal the digit in the, what we call the units place, or it's like the ones place. All right? So that means the original number is 10 times the number in the tens place plus the number in the units place, right? 1 times, you might say, right? We're multiplying to create the place value. But when we reverse it, then the number that we want to multiply by 10 is actually the units digit, and then the number we multiply by 1 is the digit in the tens place, because we're reversing them, right? Digit in the tens place become the digits in the ones place. Digit in the ones place becomes the digit in the tens place. I'm going to stop talking now. That's just confusing. Okay, let's go back and find our equations. The sum of the digits of a 2-digit counting number is 5. So that's without any consideration for their value. It's just the digits themselves. When the digits are reversed, the number is greater than the original number. There's a number, but I'm not going to tell you how many. So the reversed is greater than the original. So 10t plus u is greater than 10. No, I'm writing this wrong. The reversed is greater than the original. So this is the reversed. Here, let me just write it over. Reversed is greater than original. So he's the smaller one. And the balancing number is 9. Make sense? So this is what you need to remember in order to successfully do these problems. Okay. Now, this is a bit of a mess, so we can clean this up. Let's move the t and the u to this side and leave the plain number over there. So we're going to subtract 10t and we're going to subtract u. And we'll get 9u minus 9t equals 9. Huh. That's a lot of 9s, isn't it? So what do you say? We just divide everything by 9. And we get u minus t equals 1. And now, what if we just rearrange this so we could substitute it in? We'd be all done, right? Let's just make this t equals 5 minus u. And then we'll substitute this in down here. U minus 5 minus u, better use a bucket because we've got minus signs flying all over the place, equals 1. That one, right? Because I substituted in there. Okay, so then I get u minus 5 plus u equals 1. We better add 5 to both sides. And I'm just going to go up and finish it over here. And I get, that cancels, I get 2u equals 6. So I get u equals 3. And then I know they have to add to 5. So t equals 2. So the original number is 23. And that's the right number. Yay! Make sure you copy that. 5. We still have 3 more to go. I'm sorry. These are brutal. We're going to do a couple chemistry problems. The chemical mixture puppy dogs. Remember those? 18.5. Okay, let's read it. The first thing we have to do is figure out which type of chemical mixture problem we have. Type A is when we have the same solution, different percentages. I'm just going to make up some. And we want to pour a little of this and dump a little of that. And we want to create a new solution that is like in between. Okay, so we have a high, or no, this is a low, sorry. This is the high. We have a percentage that's too low, we have a percentage that's too high, and we want to combine them to get something that's in between. The type B is when we have something and then we either add or subtract something to change it. We evaporate or we add some buttermilk, and then we get a different percent. All right, that's where we focus on the change. These are our 2 types. So the first thing we need to do is listen to our story and figure out what we've got. I'll just tell you, spoilers, we're doing 2 of these problems, and I think there's 1 of each, yeah. Okay, let's go back. To get 1,000 gallons of a mixture that is 56% alcohol, it is necessary to mix a quantity of 20% alcohol with a quantity of 80%. It's type A, right? Because we have the different percentages, a high or low percent, and we want something in between. Now, one thing I want to tell you about these is that when we set them up, we're going to have 2 variables. And we call them P and D, right? Which stand for pouring and dumping, which is kind of silly, but it's just a little shorthand way of saying we're pouring 2 different things in, and we'll use those different letters to help us distinguish which is which. All right, so we're gonna set up this style of picture. There's one percentage, there's the other percentage. I like to make this one flatter. It looks like a robot face to me. I also like to put watermarks because it makes me feel like I'm a real chemist in a real chemistry lab, and I think that's fun. Okay, now we'll get we want to make 1,000 gallons of a mixture that is 56%. It's necessary to mix a quantity of 20% and a quantity of 80%. How much of each was required? Okay, we know that we're going to have 2 variables, a P and a D. Like the coin problems, we start first with just a simple quantity statement. The amount poured plus the amount dumped equals 1,000 gallons. Now we multiply through by the percentages. That's our value statement. 0.2 times the amount poured, because this is the poured side, plus 0.8 times the amount dumped, because this is the dumped side, will equal 0.56 times 1,000 gallons. Oh, interesting, right? Hope this is coming back ever so slightly. Now let's clean this up because I don't like it. I can see that to remove our decimals, we're gonna have to bump every number twice, aren't we? That'll become 20, that'll become 80, and then here's why we need to bump it twice. That'll just be 56. Okay, so I'm gonna fix this. It's 20p plus 80 D equals, let's see, 56 with 3 zeros. Make sense? Right, I'm ready to go to the top of the next page. Let's substitute. We can adjust one of these. I guess I always just leave the first one here and kick the second one out. So I would turn that into P equals 1,000 minus D. Let's substitute that in here at the top of the next page. So it'll be 20 times that plus that equals that. Ready? $20 times 1,000 minus D plus 80, D equals 56,000. I think I got that right. Let's hope, right? Just double checking to make sure I didn't copy wrong. Yay. All right, so we're substituted and now we'll be able to solve for D, but first we have to do just some algebra. 1, 2, 3, 4 zeros minus 20D plus 80D equals big number. Combine like terms while we swim that big, chubby, plain number fish to the other side. That's a 6. So this cancels. This becomes 60D equals 36,000. Divide both sides by 60. I'm going to divide, that goes away. Divide both sides by 10. Divide this 36 by the 6, I get another 6, and there's 2 zeros left. So that tells me that the amount that I dumped in equals 600 gallons. Interesting, right? We got it, that's right. And now we go back to the very beginning when we said that P plus D equals 1,000. And that tells us that the amount we poured in has to be 400 gallons. Guess what? That's the right answer. Yay. Okay, so that's a type 1. Again, remember that we do have 2 variables, and that means we have to have the 2 equations. In the type B problem, we only have 1 variable. Oh, that makes life so much easier, but we set up as if we had 2, and I'll show you what I mean by that. Ready? Let's do the next one. I better hurry, you guys. It's getting dark outside. I'm losing my light. This is 18.6. How many liters of a 64% glycol solution must be added to 77 liters of a 23% glycol to get a 42%? Well, we could do this as a type B. Or a type A. I would rather do it as a type A. John does it as a type B. I disagree. I think we should do it as a type A because it fits that pattern better. Okay, so back to our robot man. We're gonna pour some and we're gonna dump some. All right, let's put water in our things. Glycol is a liquid. I think it's a medium that other things can be added to. Okay, how many liters of a 64% glycol must be added to 77 liters of a 23% glycol in order to get a 42% glycol? Now, this is the amount that we're gonna pour. That's 77, we know for sure. And it's gonna have to add up to this, so the total is gonna be P plus 77, right? Usually we're given this amount. Like last time we had 1,000. Usually we're given this. This time we're given this amount. That's kind of weird and kind of different, but we can do it. So, the amount poured plus, so we can say D equals 77, we know that. Plus 77 equals P plus 77. That sounds weird and confusing, but it's going to be helpful when we go to set up the next one, because what we've got is 0.64 times P plus 0.23 times 77 equals 0.42 times P plus 77. And now we see, oh, our D went away. We don't really have a D, so that kind of makes it type B-ish. And we could have set it up that way, but I want you to see that it works to set it. I think it's more logical to set it up as an A, and then you sort of morph your way into a type B. All right, I want the decimals to go away. I don't know about you, but I cannot live with that. 64P plus, what is 23 times 77? Shall we multiply and find out? I think we should. Oh, it's not 0.23 anymore. 21, 23, okay, so this is 1771 equals 42P plus, oh, now we have to do 77 times 42. Three, two, three, four. Those are big random numbers, aren't they? All right, let's swim the P's this way. And the plain numbers this way. He's in a little box of separateness. And what do we get? That cancels, that cancels. 64 minus 42 is what? 22. P equals, now let's subtract this. 4 minus 1 is 3. 3 minus 7 doesn't work, so we borrow 1. 13 minus 7 is 6. 11 minus 7 is 2. And 2 minus 1 is that. And what we can see is that this is not going to come out real even. Right? I'm going to do my calculation on a random piece of paper. John suggests us using a calculator. I think he's a coward. John, you're a coward. I don't like it. Here's a piece of paper I can use. I was just looking for something. 1263 divided by 22. I know that 2 goes into 12 6 times. The right answer is that the amount of glucose that we need is 66.5. I don't have my calculator handy and I don't want to take the time to do the division. So I will report back to you in a short follow-up video. I'll report back to you the result of this calculation. But let's do the last problem and move on, because you want to be done with this. 18.7. This is a fancy ratio style problem. I'll read it to you and then I'll remind you of the science in it. The weight of the carbon in the container of a bunch of different things was 113 grams. What was the total weight of the compound? Okay, so what we have to do is set up a big ratio table that helps us organize all the information and find the relationships between the different chemicals. We are not chemists, but we are smart, so we can do this. The first thing we want to do is make a row for each one of the different compounds in the thing that we're given, and then an extra row for the totals. So there's a chemical called C, and there's one called H, and there's one called Cl, and that's it. That's the total. Now, in order to do this, first we have to find out the ratio of the different atoms. And John tells us this we know this by looking at the little numbers. Here, let me write down the chemical's name. C3, H7, Cl. Okay? That tells us, this is the recipe. That tells us how many of each atom we have in our soup. Okay, so there's 3 C's for every 7 H's for every 1 Cl. We don't need the total number on this. Then we have to figure out how much they weight. This is how many atoms there are. This is the atomic weight. And John gives us this information too. We're not expected to know it. He gives us this at the end of the writing of the problem, and he writes it like this. C equals 12, H equals 1, Cl equals 35. So you're not expected to know this either, right? So this information came from the recipe. Now the weights come from this explanation that John gives us. So 12, 1, and 35. Okay? This then becomes the weight of each particular kind of chemical in whatever this compound is that we're making, right? We multiply it through. We put in 3 atoms of, C is carbon, I believe. They each weigh 12, whatever they weigh. So that means it's 36. 7 times 1 is 7, and 1 times 35 is 35. Now we're ready to add up a total. Totals in this part of the problem are meaningless. We don't need these boxes. Now we're ready to add this though, and we get, what is that, 78. Okay, so that is the weight of each element, excuse me, in one molecule. Of this compound. Okay, these are the different atoms that we're using. Atoms are smaller than molecules, right? Atoms clump together in certain groupings to make compounds. So that's what we've got here. Now we're comparing the weight of the compound in one molecule to the actual weight, because we've got more than one molecule. And let's see what John tells us about that. He said the weight